Okay, so here we're going to try out a few simple questions on sketching velocity time graphs. Okay, zero velocity time. Some important points: the gradient is the acceleration, and the area underneath the graph is displacement. So let's start. Rainer starts from rest, moving north with a constant acceleration of 3 meters per second for 5 seconds. So he's moving north. So if we pick the north direction to be forwards, let's see what would happen. This is what we would do. So he's gonna be moving into the positive directions. Constant acceleration means the gradient must be constant. So actually we're gonna draw a sort of a straight line to show us a straight line because it's a constant acceleration. So the speed is increasing at a constant rate for 5 seconds. But then in addition, what else do we need to figure out? We need to figure out her speed at the end of those 5 seconds. How do we figure out her speed? In addition, we start from the zero because they say that we start from rest. That's why we started from zero. Then we want to figure out her speed at the end of the 5 seconds. So for this, we're going to use the Suvat formulas, just like we've done before. So Suvat. The initial velocity is 0, the acceleration is 3, and the time taken is 5. And we define velocity. So we need a formula that does not have the s, that only has these 4 things. What formula is that? V equals u plus at, which is 0 plus 3 times 5. Sorry, was thinking a bit ahead, which is 15. So final velocity there is 15, the end of the 5 seconds. And that's what this graph would look like. When D is moving north at 2 meters per second, when she starts to accelerate at a constant rate of 0.5 meters per second for 6 seconds. So now we have to be careful with this. When D is moving north, so she should be up here. And she's moving north at 2 meters per second. So that means at time 0, she already has a certain velocity. She's not at velocity 0. She actually has a certain velocity. At time 0, she was already at 2 meters per second. She had already started moving north at 2 meters per second when we found her. So we're not starting her off at 0. Then, after that, at time 0, she starts to accelerate. Accelerate means her speed is increasing. So we should expect it to be going upwards. But they're saying it's moving at a constant rate. So we're going to make it go upwards, but with a straight line. So, like that. And they say that she does this for how long? 6 seconds. So 6 seconds. Let's see her final velocity. Use the Suvat equations. SUVAT. Initial velocity here will be 2, not 0. Acceleration is 0.5. And the time is 6 seconds. We'll say V equals U plus AT. So which is equal to 2 plus 0.5 times 6, which will be 2 plus 3, which will be 5 meters per second. And that will be the final velocity at the end of the 6 seconds. We can also think about calculating the distance that she traveled here. Well, this is a trapezium right there. That's the trapezium. That's the area that we need to calculate here. You could also just use the Suvat equation, but I just wanted to look at it from the graph. We're calculating that area. So I'm going to say that if it's the area underneath the graph and that's a trapezium, we'll say a half times the height times the sum of the parallel sides. That's the formula for area, which equals displacement. So what is the height? The height, let's first find the parallel sides actually. The parallel sides will be that and that. The initial velocity and the final velocity and the initial velocity. Those will be the parallel sides. So 2 plus 5. And the time will be the other side, the height. Because it meets both of these at right angles. That's the height. So the time is the height. So a half times 6 times 2 plus 5. Or if you pay attention, you'll see that actually what we've done is say half, the 6 is the time, the 2 is the u, and the 5 is the v. So we've actually kind of derived the equation for displacement. Displacement is equal to a half u plus v into t, and that's how we get the equation. But remember, this equation only works for constant acceleration. That's why you see we have constant acceleration here. That's how we have the straight line, because there's a constant gradient. If there was a curving gradient, that formula would not be able to find the area underneath this graph. We would have to integrate to find the area underneath it. So that's an important point to remember. Dylan is moving south at a constant speed of 4 meters per second. So let's see this. So Dylan is moving south at a constant speed of 4 meters per second. So if we consider this as positive and that as negative, and that's 0, and that's our velocity. This is our velocity, and it's in meters per second. And this is our time, and it's in seconds. So if Dylan is moving south, well, we're gonna be down here, right there. So what's his initial speed? Let's think about it so that we know where to start from. Dylan is moving south at a constant speed of 4 meters per second. This tells us that actually at the very moment that we see Dylan, he's already at a speed of 4 meters per second. But now, should we put him up here, 4, or down here, 4, negative 4? Well, because he's moving south, let's put him down here, because we said let's pick the north to be positive. You can just make this decision all by yourself. So if he's moving south, we can take it as negative 4 as his initial velocity. And if he's moving at a constant speed, that means he's going to remain at negative 4, negative 4, negative 4, negative 4 the whole time. The whole time he's going to just be at negative 4. Even at time 100, time 1000, as long as he's moving at a constant speed. That's why the gradient of this graph is 0, which shows the acceleration is 0, which shows the speed is not changing at all. And that would be all you have to do. Which is why if you calculated this area, that would show you how far backwards he has gone. While if it was above the graph, it would be showing you how much forwards he has gone. That's it for that. Susan is moving north at 6 meters per second. So she starts out at 6 meters per second. Then what? She starts decelerating at a constant rate of 0.3 meters per second until she comes to rest. So this is velocity in meters per second, and this is our time in seconds. So she's moving north at 6. So she starts out right there at 6. She starts decelerating. She's slowing down. So if you're slowing down and you are already at 6, we would expect that at some point you're going to reach 0 meters per second, right? Because that's what rest is. So she's going to slow down until she comes to rest. She wants to come back to 0 meters per second. She starts at high and then she's coming to rest, because rest is the x-axis. She decelerates at a constant rate of 0.3 meters per second to rest. Now we need to figure out the time as well, so we're going to do SUVATS. So her initial velocity is 6, rest means 0, acceleration 0.3, but deceleration, so minus 0.3. So now we need to figure out the time. So we're going to say A equals V minus U over T, and T equals V minus U over A. We just flip those, which will be equal to 0 minus 6 divided by negative 0.3, which is 6 divided by negative 0.3. Let's see what that comes out to. Negative 6 divided by negative 6 divided by negative 0.3. That gives us 20. So it takes 20 seconds to get back to rest. And that's it for that.